Okay, Assalamualaikum warahmatullahi wabarakatuh. Today my group and I will present about experiment T2, that is thermal equation of state and critical point. Okay, first, my name is Anishaira binti Salman Steven.
I am Darren.
My name is Akila
And
binti Farahin.
next slide. Okay, the objective of the experiment is first to measure a number of PV isotopes of ethane or sulfur hexafluoride, and second to determine the critical point and critical quantities of ethane and sulfur hexafluoride, and third to calculate the constant of the van der Waals equation. Next. Okay, the apparatus we use is critical point apparatus, immersion thermostat, water bath, compressed ethane or sulfur hexafluoride gases, and the fifth is mercury tray and vacuum pump. Next. Okay, for the theory is, first, gases can be converted to liquid by compressing the gas at a suitable temperature. The critical temperature of a substance is the temperature at the above which vapor of the substance cannot be liquefied no matter how much pressure is applied. And at a higher temperature, the gas cannot be liquefied by pressure alone, and that's why as temperature increase, the pressure will increase and causing the phase to change to gas. The critical point or critical state is the end of a phase equilibrium curve, and for ideal gas we can calculate by using the equation PV equal to RT. While for the real gas we can calculate by using the van der Waals equation. Okay, let's see this diagram. Okay, the critical point is where at the T equal to T critical line intersect with the curve, that is the critical point. So for this experiment, we use ethane, and the ethane temperature is, the critical temperature for ethane is 32 degrees Celsius. So above the line T equal to T critical, the phase will change to gas, and below that it it will change to liquid. Next. Okay, for the procedure, first the temperature control bath was filled with the distilled water up to point when the heating coil was fully immersed. The temperature was set to 26 degrees. The water circulating system was worked properly by adjusting the pinch cork to control the temperature. And third, the pressure was increased by turning the pressure piston in clockwise direction until volume ethane reached 3 cm power of 3, and then the maximum pressure cannot be exceed than 50 kilopascal. And lastly, we will record the reading of temperature and volume. Oh, not less. Okay. Next, reduce the temperature, and the temperature was increased by 2 degrees as in step 2. Data collection was stopped when it reached 38 degrees Celsius.
So
Okay.
this is the data we collected. So our we are also informed to stop the data collection once the pressure reach 50 kilopascal. So first we have and these are all uh, pressure at different temperatures, and here is the volume in centimeters, centimeter cube, or in milliliters. So we collect the volume from 3.0 to 0.4, where the where we can see the pressure is reaching 50 kilopascals at here. So we can see at certain temperature, the pressure will stay the same for a for some volumes. For example, when temperature is 26 degrees Celsius, we can see uh, the pressure at around 0.9 to 0.6 milliliters, the pressure stays the same. So this goes around the same for 30, 31. But after after 32 degrees, above 32 degrees, which is above its theoretical, it attains theoretical critical temperature, we can see the pressure increase doesn't have a what we call a stable point. So here's the analysis. So after we collected the data, we plot the graph. So this is a PV graph. This this axis here represent pressure of times 10 to the power of 5 pascals, and the x-axis represent volume in milliliters. So we can see for temperature of 33 and 34, there is no stable, there is no constant pressure, but below that, we can see the pressure will mostly the same, stay mostly constant at a certain volume. So if we trace a line for the constant volume, we can see a region here. So for the peak, we can estimate the critical pressure and the critical volume. So from the data obtained, we found that our critical pressure is 49.5 bars, or 49.5 times 10 to the power 5 Pascal. So from the volume, critical volume, we obtain 0.78 centimeter cube, so which correspond to 99 degrees Celsius. But in theoretical value, is a bit lower than that, our critical pressure, but our critical temperature is very differs a lot from our what we obtain. So the errors of critical pressure is 1.3, about 100.4%, and our critical temperature error is 22%. So our C- uh, our critical volume we obtain is 0.78 centimeter cube, and so our A we got 90.26 milliliter squared per milliliter squared bar per mole, uh, and our B is 0.26 cm centimeter cube per mole. But this differs a lot from our theoretical values, as you can see here.
For this discussion, the data obtained in the experiment was plotted to determine the critical point of ethane hexafluoride by the series of by the isotherm PV diagram. The isotherms below 32 degrees Celsius are characterized by a plateau caused by the liquefaction of the gas. The point at which a plateau no longer occurs is the critical point. The point at which the graph obtained in the experiment show that the volume V gradually increase and the pressure at constant temperature decreases. Once the pressure reach saturated pressure, ethane hexafluoride start to boil and the pressure remain constant until the evaporation process is done. This process occurs at saturated region. The pressure decreases after reaching saturated vapor while the volume increases. Next. After temperature get higher, the as the saturated liquid and saturated vapor state increase and form a dome, which a region in the graph. The peak of the region is known as critical point. The critical point is a point which saturated liquid and saturated vapor state are identical. Above the critical point, there are no distinct of phase change process. The critical temperature in this experiment is 372 Kelvin or 99 degrees Celsius, and the critical pressure is 49.5 bar. Uh, eh, in this experiment, we use van der Waals equation to obtain the van der Waals constant. There are some deviation between theoretical and experimental value of critical temperature and critical pressure. The deviation is due to some errors occurs in the experiment. Errors. uh, there are errors. Sebelum slide. Okay. Okay. The first error is we use mercury in this experiment. Mercury has the tendency to evaporate into the environment, causing inaccurate data obtained. Second error is the thermometer used in the experiment. The thermometer requires more time to get a constant temperature. The third error is parallax error due to incorrect eyesight when taking the reading. Lastly, the pressure of exceed 50 kilopascal and the reading are not exactly in a static place, which make the data less accurate. For the precaution, uh, we could use thermostat instead of thermometer because thermostat has smaller scale and it will give us precious readings. The second precaution is sit in the correct position so that our eyes is perpendicular to the scale of the instrument. The and the pressure in this experiment need we need to make sure that it should not exceed 50 kilopascal. For the conclusion, the PV isotopes graph was plotted to determine the critical point of ethane hexafluoride. The critical temperature is 372 Kelvin or 99 degrees Celsius, and the theoretical pressure is 49.5 bar. And the van der Waals constant is for critical value is 0.78 centimeter cube. A is 90.26 milliliter square bar per mole square, and B 0.26 centimeter cube per mole. Okay, that's all.
Okay, that's all from us. Thank you.